This is Unit 9 of AP Physics C, Electric Potential, for our AP test exam review. So if we have two positive charges, electrostatics tells us that, hey, these two positive charges are going to repel each other because they're like charges. And we know that the electrostatic force is going to equal, K, so if this is big Q and little q, right? The electrostatic force of repulsion will be K times big Q little q over R squared. Now, let's say that this charge moves. So initially it's like a distance R. Let's say it starts actually a distance RA, and it moves to a distance RB from the big charge, right? And maybe the big charge is like fixed in place, and the little charge gets repelled away. And we want to calculate the work done by the electrostatic force on the little charge. And obviously our most basic equation for work is force times distance, but we can tell by the electrostatic equation that as the distance changes, as the two charges get further away, the force will weaken. So we can't use that force times distance equation, right? It's not a constant force over that distance. So we're gonna have to take an integral to find the work. And it's not a terrible integral. If you're looking at the work done, it's gonna be the integral from RA to RB of the electrostatic force over R squared, or dr, right, with respect to the change in R, the change in distance. So if you work out this integral, it'll end up being K big Q little q over RA minus K little q big Q over RB, right? If you think about the integral, the antiderivative of 1 over R squared is negative 1 over R. So then when you plug in your bounds, the negatives will kind of swap, and you get this expression right here. So that's pretty cool, right? So if you know the charges, the initial and the final distance, we can figure out how much work was done on that charge, and whatever that work was being done, it got added to kinetic energy, or the work, like the work was the change in kinetic energy, right? So you can equate this to 1/2 mv squared, solve for speed or whatever. But another kind of interesting thing that we can kind of do with this is, well, we know that the electrostatic force is a conservative force. And what a conservative force means is, regardless of the path, right? So regardless, let's do it over here, right? Regardless of the path that this charge took to get to this spot RB, regardless of that path, the work done on that charge would be the same as if it had just went a straight line to that point. That's what a conservative force is. And this should intuitively make sense, right? Because the entire time along this path, right, the force would be pointing away from the along this path. If this arrow represented the force on the charge along its path, it would always be pointing away. So as you got closer to the charge, it would be doing negative work because it's a force is in the opposite direction of displacement, and as you got farther away, it would be positive work because it's in the same direction. So the net contribution of all those works would end up being, you can see it, you can see this path is longer going that way. It would end up being just this quantity, which is the work from going to RA to RB, right? It's a conservative force. You can prove it mathematically. I've done that in a video. Point is, it's conservative force, and what we can do with that is when we can basically say that, hey, well, the work done by any conservative force is always going to equal negative change in U. So what this means, what this equation is saying, the change in potential energy, right? It's just saying that if you have a conservative force, that conservative force, its work done can be it can be the same as like a potential energy, right? So if you think about UG and U spring, the reason those potential energies exist is because they're associated with forces that are conservative, right? The spring force, the gravitational force, those are conservative forces, and thus they have that like potential energy related to them. So the work done by conservative force is just the negative change in U, or the change in potential energy associated with that force. So we can just kind of set these equal to each other, and we can say, well, this KQ, KQ little q over RA minus K big Q little q over RB, well, it would equal the negative of, if you took the final potential energy, right, of whatever potential energy is associated with this force, right, we can call it the electric potential energy. We could do U final minus U initial. So hopefully it makes sense what I'm doing here. What I'm really doing is I'm showing that, well, when you distribute the negative, you have negative U final, and then the negative times the negative here equals plus. What I'm showing is that this positive U initial is really just the positive term right here, and then negative U final is just the negative term right there. So I just kind of proved, or not proved, I kind of derived that the electric potential energy at any point will just equal K Q little q over R, right? Because, if this was the initial potential energy at RA and the final was at RB, right? That would make sense that RA was where it was initially at, RB is where it ends. So any kind of potential energy at any point will follow this formula right here. So that's kind of what I did here, is I derived that expression. Now, this equation is pretty nice, and it looks very similar to like the UG equation. And if one of these charges is negative, it ends up becoming the really just the UG equation with the negative, right? Because if you have a positive and a negative, well, first of all, if you have a positive and a positive, right, all the energy is initially, right? So U initial right here is initially all the energy, right? The total energy. And then if they go far, far, and far away, right, then the energy being stored is just U final, right? Whatever that U final is, if you were to calculate it using this equation, plus the kinetic energies for each of them, right? And by conservation of energy, no work was being done on the system of these two charges. You could set the initial quantity equal to the final and solve for whatever you need. And for a negative, right, and obviously as R approaches infinity, U final becomes 0. Because we have an R in the denominator here, right? And this would all the energies would be positive, but as soon as you have a negative, right, so if a positive and a negative charge, all the energy is still U initial, but now it's going to be some negative quantity. And as they get closer, which will happen, right, because they're attracted to one another, well, now you have U final. And even though you might think like, oh, well, the distance got smaller, so shouldn't that be more potential energy? That would be true if it were positive, but because one of these charges is negative, right, it would end up being a negative potential energy, so it became a bigger negative number, right? And when you're dealing with scalars, a bigger negative number, that's just like a smaller number, right? It got more negative. You have less energy here than you had here because it's more negative. So plus K final, you can solve for whatever you're looking for. And as the initial distance approaches, as our initial approaches infinity, where they started here, then your U initial just ends up being 0. So that's kind of, just conservation of energy stuff. So if you could have problems where, I won't walk through them just for time's sake, but if you are curious, let me know. I could approach some problems like this. Essentially, a type of problem they might ask is, well, let's say you have a Van de Graaff, right? A Van de Graaff with some amount of, charge, right? And they give you that like big Q, right? That would be a number. And they have now, let me actually draw it like more like this, right? And you had a negative charge, or like an electron, right? Just headed towards this Van de Graaff with some speed v, right? And let's say it has a mass m and a charge q, and these would be negatives or whatever, right? Point being that let's say that it starts at a distance r initial, and let's say they ask what is going to be the distance of closest approach for the little charge, right? Because as it gets closer and closer and closer, there's a bigger and bigger repulsive electrostatic force. You can intuitively imagine that it's going to eventually slow down and come to a stop right here, right? And then start going the other way because of that repulsive force. And you can solve for that initial distance by using energy. You would just say that, well, all the initial energy is stored as U initial plus K, right? So all the initial energy is stored electrically and kinetically. And at the end, the final energy is all electric potential energy. There's no more movement. It's got to its distance of closest approach where it's no longer moving. So you would have your U final. And then you could just then plug in numbers, right? So KQQ over R initial plus 1/2 mv squared would equal K big Q little q over R final. And then you could just do some algebra solve for R final. And let's say they ask, well, what would its speed be after a really long time where it rebounded and then started going the other way and it's a really long distance away? Well, that's our case where when R is infinity, U final is just 0. So you could say, well, and all the initial energy at the point of closest approach is U, right? Like all electric potential energy. And at the end, there's no more U final because it's R at infinity, right? A really far away distance. So all the energy is K. So then I can just use this quantity as my U initial, right? Because that's the new starting point when it's at the closest approach. And they're all equal, so you could use that quantity right there, whatever's easier for you. And then 1/2 mv squared solve for B, right? So just some conservation of energy stuff. Just wanted to just show that could be on the test, right? So, we talked about potential energy. Now, what on earth is potential, right? You're hearing about potential energy, and potential sounds similar, but what exactly is it? Now, for electric forces and fields, we use the electric field as kind of like a way to kind of model electric forces in a way. And it was kind of a way for us to be like, well, if you had a certain electric field, it could have a certain strength, and then the actual electric force by a charge, right? If you were to put a charge in that field, the electric force would kind of change depending on the magnitude of that charge, but it's proportional to the strength of the electric field. And potential energy kind of has a similar idea called potential. So electric potential, potential V, that's a symbol we use, is the amount of electric energy, or electric potential energy, really, per charge, per unit of charge, right? So if, let's say, in this example right here, where I have a positive charge, big Q, right? Let's say I don't really put a charge there, but I want to see at this point, if I were to put a charge, right, at point P, which is a distance R away, right, what would the electric potential there be? Well, the electric potential at that point is really, if we imagine so it would equal, so the V would equal just the electric potential energy at that point, had we put some sort of test charge there, right? If we imagine putting a test charge there, then the potential at that point is just the amount of energy that test charge would have divided by whatever that test charge is, Q initial, right? I don't know what that test charge is, but it's this ratio between the electric potential energy and that test charge that I put there, right? If I increase whatever charge I put at point P, then the energy will also increase because it has more charge. But that ratio is really the electric potential. So if I write electric potential energy, right, K big Q times the test charge over R, right? I'm just canceling out that Q initial, and I get that V, the potential, is just KQ over R, right? So if I increase the actual charge creating that potential, right? Whatever, so this is the big Q is the charge creating potential, right? This is the charge creating the potential. So if I increase that charge, then yeah, there will be a larger potential. If I increase the distance from like the point that I want to measure the potential at, right? If I increase that distance R, the potential gets smaller. So hopefully that kind of makes sense, right? It's like a ratio in a way. And you know, another way we can express this ratio is that U is equal to Q initial times V. So this Q initial represents the charge at that potential, right? Charge at potential, V, right? Whatever that potential is, if you take the charge at that potential, multiply it by whatever potential it's at, you get the amount of potential energy it has, right? So, and you plug in this equation, then boom, you just have the potential energy equation. So, couple things. Well, then I know that if I have U final, let's say I take a charge, the charge RA, I moved it to a different potential. So the change in U, right? So our U final minus U initial, that's just the same as Q initial times change in V, right? Because I didn't change my charge when really what I'm doing is U final minus U initial, and that's going to equal Q V final minus Q V initial. And you could factor out the Q there and you get change in U equals Q times change in V. The change in V is what we call a voltage. So this is actually what voltage is. It's a potential difference, right? So voltage, aka potential difference. And when we get to circuits, you know, it's the idea that voltage is a thing that causes charge to move, and it's kind of related to energy, right? If you have charges going between potential differences, it's going to be moving, right? Like potential difference causes charges to move. So what we can finally do to get our final equation is relate work back to this. So work, if you think about work is equal to negative change in U, well, work was really just this integral right here, right? RA to RB of K big Q little q over R squared dr is going to equal negative Q times change in V, right? So with this thinking, if you drop a Q, right, from both of these, both sides, and this is, you know, that Q on this side is a constant, so I could just drop that from the integral, or integrand, whatever. You get, now this negative change in V is just equal to this quantity. Well, this KQ over R squared dr, that's just the electric field being integrated with respect to R. So RA to RB, E dot dr is going to equal change in V, right? So for a uniform electric field, if you take that out the integral, you just get E times change in R equals change in V, which you will see how that kind of comes into play in a second. But really this is just saying that, well, if you take the force and integrate it, you get the total change in potential energy. If you take the field and you integrate it, well, you don't know what charge will be moving across that field, right? You don't know what that test charge is. So that quantity will end up being the voltage, because for the voltage that you get, well, it'll be the negative voltage. For that voltage, like, you don't know what charge is going through it, so you can't really find the change in potential energy. But voltage is like the change in potential energy per charge, so you don't need to know what charge there is for that, if that kind of makes sense. You know, positive charges will naturally go from high to low potential. So if you think about a positive charge here, right? If this was the potential here is some positive number, and then it goes far away to a lower potential because that R got bigger. And let's say it was a negative, right? Let's say it was a negative charge that was creating the potential. Actually, no, let's not do it there. Let's do it here, just that original example. If for whatever reason it was a negative, then now it starts at a high potential, and the potential is negative KQ over R, because now it's a negative creating the potential. As it gets closer, it's becoming a bigger negative number because the R got smaller, but now it's negative. So it's still going from high to low potentials. Electrons are reversed, right? So if this was a negative, it starts at a certain negative potential, and then it goes farther away to a less negative potential, right? Because now this is kind of like hard to think about, but if this is negative, the R got bigger. It's less negative, but that's a higher potential now. So electrons go from, or not electrons, but negative charge in general goes from low to high. And yeah, so if we think about, or one last thing I kind of want to show is that, well, also we get that work, you know, if we go back just to this step right here, we really get that work is equal to negative Q times change in V. So if we know the potential difference and the charge, we can get the work being done. And like visually, one way you can find potential difference is through equal potential lines. So charges, right, they create potentials all around them. And I'm going to kind of erase this stuff. Yeah, I'll erase this stuff. But they create potentials all around them. So if I think about, well, a positive charge right here is going to create a potential right here, right? And the potential at this point, we can use our KQ over R to really calculate it. But the main idea is that, well, if this is a distance like R initial away, then at a distance R initial here, it would also have that same potential, right? So if I moved, right, and it would be, hopefully you understand, you know, same distance, so the KQ over R quantity, that would be the same. So if I move a charge, like, let's use a blue color, I guess, to show this. But if I were to take my charge, if I put a charge here and I moved it on some sort of crazy swiggly path to that point right there, well, the potential difference, right, would be zero because the potentials at this point are the same. So the work would be zero. And with that thinking, if you took all the points that are equidistant, right, you would get a circle. And on this circle, because it's equidistant from the charge, all these points would be at the same potential, right? Whether this is 10 volts or 20 volts, I don't really know, but it would all be at the same potential. So no matter if I took a charge and moved it anywhere along this point of the circle, the work being done by that force would be zero, right? So with that thinking, there would be a bunch of circles that are at the same potential. And each line just indicates that everywhere along that line, the potential is the same. So maybe this is 10 volts, maybe this is 5 volts. And if I were to now move my charge from here on some sort of crazy path to this point, doesn't matter the path, right? I just know my potential went from 20 volts to 5 volts. That's a negative 15 volt. That's a negative 15 volt drop. So the work done would be, it would really be that charge times negative 15, right? So, well, that wouldn't really make sense. I have to refresh the sign notation, right? I forget if potential difference is V final minus V initial or the other way around. If it's V initial minus V final, then it's 15 volts, right? Because I'm going in 20 minus 5, and then 15 times the charge, that would be negative, right? So it would be negative work being done by the force, but the force that actually got it over here, that force would have done positive work. But the electric force did negative work. So I need to, think about how forces are doing work, and how it'd be negative and positive, I'll maybe make a comment and make a note about the negative here. Point being is the main idea to take away from this is that equal potential lines are lines where the potential is all the same, and you can use it to figure out work and other stuff. And you can get crazy equal potential lines, right? Maybe you have a really weird charged object that's making an equal potential line somewhat like, this or something. Still works the same, right? Everywhere along that point, the potential is the same. And if I know the different, voltages, whether it can also be negative too, right? If I know that stuff, I can figure out the work and stuff. And the electric field, hopefully it kind of actually makes sense that it's always perpendicular to the potential lines, right? If I were to draw, this would be kind of crazy. If I were to draw the electric field, it would kind of look like this, right? Because if the electric field is perpendicular, that means along this path, the electric field line is always perpendicular, so it's never going to do any work. That's why you remain at the same potential. If it weren't perpendicular, that would mean work is being done and you're somehow not at the same potential. So that's why they're always perpendicular. It's just a work thing, right? Whew! That's basically all the concepts for electric potential. I just want to review two things. Two key ideas about potential before we really, kind of finish this off is, well, we talked about potentials due to point charges, but you might not always get point charges. You might get, something like a whole rod full of point charges, right? Something like that. Or really thin rod, so it doesn't really have much thickness to worry about. And let's say it has a charge positive Q, and we want to figure out, well, what is the potential at kind of that midway point? Well, not midway point, but at kind of halfway in between the rod, a certain distance, like X away, right? Well, you might not really be able to use KQ over R, right? Because now this isn't made up of a point charge, it's made up of a bunch of point charges. So there's and let's say this, if this was like the y-axis, right? This, we could say negative A, and this is a length A. So the whole total length is 2A. Now you have a point charge right here, like a certain dq, that's creating a potential at this point, right? And what we need to do is sum up the potentials created by all of the dq's. We have to take an integral, right? So it would essentially be dV, right? The volt or potential created by a really small dq over R. And we have to integrate that. So first of all, if this is uniformly distributed, that means there's a certain charge density lambda, right? So let lambda equal Q over 2A, which is total charge over total length. Then I know that Q over 2A is going to equal dQ over d. Well, we're integrating, so this is kind of weird. We're not, well, yeah, it's R, right? But it's not really dr, it's dy, right? Because we're integrating along the length of the rod, which is on the y-axis. So the R variable right here is really square root R squared plus Y squared, right? Wow, this actually might be a more complicated integral than I thought. Will it? It might not actually. We'll see. I can basically get that dq, right? If this quantity is lambda, dq is just lambda dy, right? Because this right here is lambda. So I get dv is equal to k lambda dy over square root R squared plus Y squared. And we can integrate, and I get that v is going to equal the integral from negative a to a, k lambda dy over square root R squared plus Y squared. Is that a simple integral? That might not be a simple integral. It might not be as simple of an integral as I thought. I was hoping it would be a more simple integral. You know what, let's just do a more simple one then. If we had pretend we had a whole ring of charge, right? And this is a semicircle with a radius r initial, right? And this is not a part of it, but this is just the distance. Now, and let's say it has a positive charge q, right? And we want to find the potential at this point p. Now, it's the same idea, right? We're doing dv equals k dq over. Now, this time it's kind of nice because it's always r initial, no matter what your dq is, because it's a semicircle. And your dq is just that same k, well, it's the same lambda dr, right? As you integrate now, it's already dr though. Actually, yeah, it could be dr. Because you're not really integrating with theta, you're just integrating along this length. So then if you were to integrate this from 0, oh, but that won't work. Shoot, why am I forgetting this? I promised myself I was gonna wing this, and then I just realized, yeah, I might have to take some angles. That's unfortunate. Ain't that unfortunate? Let me see. Let me find. Let me see if I did this in my packet somewhere. Okay, let's do it another way, right? So, oh wait, maybe it is just 2 pi r initial. And then you pull out the k lambda r initial, that's all constants times, well, this is just 2 pi r initial, that crosses off. I get 2 pi k over, because lambda is just q over 2 pi r. So I get kq initial over 2 pi r. I just get kq initial over r initial. Does that seem right? Oh, I guess it's not. It's really, we're integrating to pi. So you gotta watch out for that. But is it that simple? Maybe it is. I don't know. I'll fact check, find out. It's definitely more simple than our electrostatics one, because voltage is a scalar, so I don't have to worry about the direction of voltage. I can just integrate and find that scalar quantity, which makes it a lot nicer. Last thing I want to show you before we're done is a bit more of a Unit 8-9 cumulative problem. Let's say we had a whole line of charge, right? An infinitely long line of charge that we might have seen before, right? So it's like a skinny cylinder, right? And it's infinitely long, right? So let's say we have a charge of mass m and charge q, initially a distance r initial, and we need to derive an expression for the closest approach r final, right? So, this is all positive, sure. And let's say the rod itself has a linear charge density lambda, and yeah, right? How do we go about doing this? Well, if we want to find the distance to closest approach, it's definitely a conservation of energy problem. And all the initial, so here's the deal, right? You could do, there probably might be a way to do this in terms of potential energy. But instead of really thinking about it in terms of potential energy, which you'll see why in a second, what we can do is kind of say, well, okay, all the initial energy is stored as kinetic, and there's going to be some work that's going to be removed by the rod, right? By the repulsive force from the rod that would end up making the final energy equal to 0 by the time it gets the closest approach where it's not moving anymore. So I know that, well, the 1/2 mv squared is just going to equal the work done by the rod, which is really just 1/2 mv squared. This is really just the same thing as Q times change in V. And we know that the change in V is just the negative of the integral from R initial to R final of the electric field dr. Why would we care about this? Well, we know that the electric field, we can use Gauss's law to find that, right? Because we know electric field dr due to a cylinder, well, not due to a cylinder, but the electric flux, right, integral EdR, is just going to equal Q enclosed over epsilon naught. You can imagine a Gaussian surface, surrounding this whole thing. You can imagine a Gaussian surface. It's going to be a cylinder, and the surface area would just equal 2 pi RL, and the Q enclosed will be lambda times L. The L is dropped, and we get that E is an equal lambda over 2 pi R epsilon naught. So if I were to take the integral from integral negative R initial R final, I would essentially get lambda over 2 pi R epsilon naught dr. And this is a pretty simple integral because the lambda, 2 pi epsilon naught, those are all constants. So you're just taking the antiderivative of 1 over r, which is just natural log r. So this will be negative. So we could pull out the lambda over 2 pi, and we can over epsilon naught times ln r final minus ln r initial. Distribute the negatives, I get lambda over 2 pi epsilon naught, and then I would have ln r initial minus ln r final, and then it would be lambda. Well, I guess technically this gets confusing though, because you put in the negative, because this would result in a negative number. So I guess we drop the negative. I gotta clear up on the negatives, and I'll maybe make a video. But I guess use your brain, right? Like, don't memorize, because whether it's like the negatives, like the work done by an external force or by the electric force, like don't just use your brain, right? Like I use my brain. I was kind of like, I don't know if that'll be negative, and then everything kind of works out because I get ln r final over r initial, which means a positive quantity right here, which kind of makes sense. So 1/2 mv squared is going to equal Q times lambda over 2 pi epsilon naught ln r final over r initial. Oh boy, you could do mv squared. This 1/2 would drop off of the half there. mv squared over pi epsilon naught over q lambda is equal to this ln. Exponentiate everything to the e power. That drops that. So then I get r final over r initial. So then it would just equal, oh, but then you need the negative, I believe. I think you would need a negative. So there would definitely be a negative somewhere. So maybe you do need the negative. Okay, I'll brush up on the negatives. But once again, right, use kind of your brain. You can kind of be like, well, I know that this R final will be less than the R initial, so it has to be a negative exponentiate, or, negative in the exponent. So yeah, that's kind of the problem I just want to show you, a little cumulative type problem. Thank you for watching this, and I'm going to try to make these videos shorter.